The mean value theorem for integrals, guys, simply says this. In other words, somewhere the instantaneous height equals the average height. And that is expressed by that relationship above. I hope, based on what we did before break and you guys watching the little review video, I'm hoping that the expression on the left looks really familiar. What would you guys say that is?
The average of the function.
Yeah, the average value of, in this case, f of x. So, average value of f of x. And then on the right, f of c, well, that would have to be a y value at a particular point. Whenever x is c, y is whatever, we're saying that somewhere the average value of f of x equals the value at one point, or you could say the instantaneous value. So in other words, we're saying your height, if you went from 18 to 69 and your average was 58, then at some point in there, your height had to be 58. You have to hit your average at least once. This example that I'm about to give you is not quite as good because the data is not discrete. The data could be not continuous. It's basketball season. Let's say that I was on the basketball team and I was kind of bragging about how awesome I was. And I said, after a couple of games, I'm like, guys, I hate to brag and everything, but I'm averaging 25 points a game. You should come watch me play. And so you come watch me play. And the first game you watch me play, I score like 3 points. The next game, I score like 1 point. The next game, I score 5. The next game, I have a really good game, and I score 11. Wouldn't you start to doubt my claims a little bit? But if I claim that I averaged 25, and you show up, and the first game I score 20, you'd be like, yeah, off game, not bad. Next game, I scored 26. Next game, I scored 23, and then it was 28. And then eventually, if I played enough games, wouldn't you expect me to actually hit 25? That would actually lend a lot of credence to my claim that I scored 25, or that I averaged, 25. And so whatever your average is, wouldn't you expect to hit that average at least once? As long as the data, as long as the information you have is continuous. Okay, so there's one condition here, and it is right here. I think it's listed a couple different times. But the condition for this mean value theorem for integrals is continuity. As long as you have a continuous graph, you got to hit your average. Got to hit your average. Okay, so I would like to help you guys set up number 11. I'm going to let you guys kind of explore a little bit with it. Look at number 11. It says, step 1, find the average value of the function on the interval. So let's get that set up and make sure you guys are good to go with that. What do you think it would look like if I was going to find the average value of that function on that interval? Any suggestions? I'm not sure what you mean by put it into this.
I don't know what it's called. What do you call it? F of C.
So I'll put it.
What do we call that? Yeah, what do we call that?
So are you talking about kind of the formula?
Yeah, like
I'd say that that's the average value of f of x formula, or the average value integral sometimes. Yeah.
Do you have to prove it's continuous?
We'll get to that in a second.
Okay.
We will. So, okay, so a second ago I said, if you were going to find the average value, like it asks you to, what would you set up? Here's what I was hoping you would say. 1 over b minus a. Does that make sense? Getting my b and my a from the interval, times the integral from a to b, so negative 1 to 2, of f of x, 4x cubed minus 3x squared dx. So that right there, that is the formula, that's the setup, the expression, whatever, to allow us to find the average value of f on that interval. Make sense? Mm-hmm. Okay, yes ma'am.
If you were solving for that, would you just solve for the integral part and then multiply it by the 1 over 3 at the end?
Yep, I would do that at the end. Yep. Okay, so I want to give you guys a couple of minutes to work through this. I think I'll work quietly up here. I'm going to use FTC1, et cetera, et cetera. this will be hopefully good review for you guys. So try to evaluate this. I'll just do this quietly. We can compare notes here in a couple of minutes. Okay, so I've got the value for this integral up there, the steps worked out. Once you're ready, feel free to check that out. Kind of squeezed in the final value at the bottom there. So the basketball one, so I preface that by saying the basketball one is not great because you can't score 25.4 points in a game. Right, so by its nature, like your scores in a basketball game are going to be continuous. You can only score integer number values. So that's why I said it's a great example, but like if I made that claim and showed up and I never even came close to the average, I'd be like, I don't think that's really your average. So when you have something that is continuous, and you can say, well, whatever it is, it's a decimal I have or whatever, you better get the average. So like our height is a better example because whatever your average height for your life is, say it's like 51 inches or something like that, and you're like, well, you know what? Really, that's my average height, then you'll what's that height? It's like, yeah, you were, because your height, unless you have this way of like, instantly your height, like people who are you can't have that.
There are 5 teams.
So your objection to basketball analogy is warranted for sure.
Oh, then you could find C. Then you could find C.
You bet. Are we guys doing okay with 2? Hello? Yes, 2? So, this is a classic case of we set something up, we did a good job, we did an antiderivative, we did FTC1, we got to a finishing line, it'd be tempting to be like, done, moving on. We really haven't answered the whole question yet, right? So let's keep reading. The question says, find the average value of the function. That's what we just did, right? So this right here, this is the average value of f of x on the interval from -1 to 2. We found the average value. And then it says, and all values of x on the interval for which the function equals its average value. So this is kind of a second leg in the journey. So the first thing we have to acknowledge here is what Marguerite brought up. We have to at least consider the continuity of this function. So is f of x continuous?
I don't know. Yes.
We do know.
Yes.
Is it or not?
Yes.
Why is it continuous? Polynomial. Yep. So f of x is a polynomial. Therefore, it is continuous. Got a continuous graph. Therefore, we can use this mean value theorem for integrals. And here's all this is. Mean value theorem for integrals says that somewhere the function has to equal its average value. We just found the average value, right? It's 2. So all we really have to do here is say 2 equals 4c cubed minus 3c squared. If you want to leave the c's as x's, that's fine. We're just looking for this value of c somewhere in the interval where the function actually hits its average, which we know is going to happen because it's a continuous graph. We're just looking for where this happens. So this would be your equation, setting the average value equal to the value at any point. I think we'd use the calculator to solve this. So if you guys would, grab your calculators, either use the intersection finder or the zero finder, depending on how you want to rearrange this if you do. And let's figure out which value or values this function actually hits its average. Anna, do you think you have it? Maybe?
More than one.
I don't remember. It's possible because this is a cubic. There could be more than one.
I got 1.137.
1.137? And that was the only one? Okay. It could just be that there's one. I don't know.
But I didn't do it by graph. I only see one with the graph. I did polysimul, like the root founder.
Oh. I'm not sure what that is, to be honest with you.
What did you say?
Did you use Bailey's calculator?
I have it on, it was on mine too, I just don't have mine.
Is that an app or something?
Yeah. Mine too, it was the, it was the. I thought the same thing. It was like
1.297. Am I in the wrong mode? Shut up. Good. I don't know that. Oh wait, I know what I did wrong. I put it 4 instead of a 3.
I'll do it.
Oh, wow. Okay, so it's just a program.
Yeah, but it's just.
Instead of graphing. Okay, yeah. I'll get you in there. Interesting. So Anna, you bring up potentially a good point, because sometimes people would be like, well, isn't that cheating or something like that? The truth is, if you set that equation up and the calculator is active, I really don't care how you solve it.
Yeah, because there's a lot of.
There's lots of ways you could do it. I just care that you could show me what you're doing and hopefully get the right answer too. Yeah. So did Anna get the right answer? Is that right? 1.137?
Yes. Correctamundo.
Correctamundo even. Okay. That we're good?
Yeah.
Okay, cool. Any questions from anybody? Okay, awesome. So, if you guys would flip forward, we're going to take a look here at one brief yet very important topic, and then we'll be into kind of the final leg of our journey with section 4.4. I think we'll have spent like 5 days by the time we're done with section 4.4. So here we go. We're going to be looking at what is called the Fundamental Theorem of Calculus Part 2. This whole time I've been talking about FTC 1. We've done a lot of stuff with FTC 1. And of course, that had to beg the question that there would be an FTC 2, and there is. So I am going to show you the trick, and then I'm going to explain the trick, and I'm going to tell you that pretty much the only way to do these is to use the trick. When was the last time a math teacher said, for goodness sake, just use the trick? Don't even bother trying to do the long way. Like, I'm not kidding. Like, if you try to do the long way, you're doing the wrong thing, okay? I want to prove to you that this works, or at least give you a sense of how this works, but then I'm going to strongly encourage you to use the trick that I'm about to show you, okay? So take a look at the blue box up here. You guys see there's kind of some unique notation, and it's really important that we recognize this notation, okay? So what does this mean right here? This means it's ddx, and you said what, Andy?
Take the derivative of.
Yeah, take the derivative of whatever shows up next, right?
But isn't that going to be the anti?
But here's the thing, yeah, it's the derivative, and you're like, okay, cool, I'm going to do the derivative of something, and then you look in here and you're like, whoa, It's the derivative, and what does the tall skinny s mean? Antiderivative. So we're doing the derivative of an antiderivative. How do you think those things are going to interact? They're going to cancel each other out. And so then when you look at this, you're like, whoa, okay, so d dx of this antiderivative, those should totally cancel out. And so then when you look at this answer, you kind of think, whoa, that actually makes sense, doesn't it? Yeah? But then some curious things show up. You start to look at this and you're like, whoa, wait a minute.
Yeah, where does f of t become?
T's, like how did t become an x? Because t is not x. It should be important. We should know like why something changed from this to that. It can't just happen magically. And that's what I'd like to show you here. Is that okay? So I'll show you a couple different aspects of this. And I'm just going to try to do this over here, like so. So check this out. I'm going to start off by saying d dx. I'm just going to start off with the original. Integral from a to x of f of t dt. So a couple things to note here. This a stands for, this is really important, stands for a constant. So 2, 3, 10, doesn't really matter which constant it stands for a constant. So instead of trying to apply this trick, I am going to try to do this the long way. And because we're doing this symbolically, this will actually be pretty doable.
What does it mean when there's an x? Does that just mean any x value? Like a constant to any?
Yeah,
No,
so
it's the
a would be like a
base x.
3, so it'd be the integral from 3 to some variable. The variable could be whatever. Kind of like the accumulation function I showed you in the little review thing. So, okay, so I want to do this step by step. I'm going to go ahead and follow the order of operations. I'm going to start on the inside. So we're going to use some notation that we haven't used in a while. I tried to make that clear that that's a lowercase f. Yes? So we don't use this notation often, but the antiderivative of lowercase f is often shown as capital F. Yes? So what I'm going to say is that this is d dx of capital F of t evaluated from a to x. Is that okay? I've just done an antiderivative. I still need to do the evaluation from a to x. So capital F means it's the antiderivative of little f. Let me keep going. So now what I'm going to do is go ahead and evaluate and subtract. So this would be capital F of x minus capital F of a using FTC1. And now that I've done all that work on the inside, now I can actually do my derivative. So what would you guys guess d dx of capital F of x would be? Yeah, lowercase. So this would be lowercase f of x. And then if a really is a constant, what is capital F of a? You're getting too far ahead of me. What's capital F of a? Not. No, you guys are doing derivatives of things. I don't want you to do a derivative yet. Like literally, if a is a constant and capital F is some function, what's capital F of a?
Number.
It's maybe some other constant. It's some number.
So wouldn't it just be lowercase f of a x?
No. So this, if a is a constant, then f of a is also a constant. And what's d dx of a constant? 0.
0.
That's what you guys kept on saying 0 because you're doing derivative of it. And I know that that's right. It just wasn't quite the question that I was asking. And so if you wanted to, you could put minus 0 right there. But why bother? Does that make sense? Your mouth says yes. Everything else about you says no.
Is that just a rule? Can we try it?
Is what just a
Does it
rule?
matter if
That
like
if A is
that
a
one
constant,
constant
put it into a function, it, like,
Yeah.
value is a constant?
Yes. Yeah, think about it. Like any,
Am I just overthinking it?
I think you are. Like think back to any, like f of x, g of x,
Oh, never mind, yeah.
like all of those functions you learned back in like algebra 1, algebra 2. If you, like whatever those are, I'm assuming they're in terms of x. If I have you find f of 3 or g of negative 7 or whatever it happens to be, aren't the results of these guaranteed to be a constant? Now we have no idea what they are because you don't know what the rule for the function is, but those have to be a constant, and the derivative of any constant, of course, 0. Yeah, okay. So Santi, maybe to help you, I want to show you.
Can we just try it with one?
I want to show you one extra level to this, and then we'll try one. We will. So let me show you a little bit of a different look to this, and it's going to be this. It's not going to be that much different. It's going to be, what if that upper limit wasn't just an x? What if it was slightly more complicated, like 3x squared, or 5x plus cosine of x, or something more complicated than just an x? I'm going to represent this with the letter u, where u just stands for something more complicated than just an x. Let's think about how this would go. And so, Santi, I'm going to go back over this again. So whenever this doesn't make sense, you tell me. Okay. So the antiderivative of lowercase f is still capital F. In this case, capital F of t. And we are evaluating from a, which is a constant, to u, and u is some function in terms of x. Could be simple, could be complicated, we don't know. Still good? Okay. So now we're going to use fundamental theorem 1, which says we need to evaluate at the upper limit and evaluate at the lower limit and subtract. And now what I'm going to do is I'm going to differentiate. And this is where this one's a little bit different. Remember that u is something a little more complicated. So I'm going to say that d dx of capital F of u, wouldn't it be lowercase f? So it'd be lowercase f of u. But now that u is a little more complicated than just an x, what has to be multiplied by? Du dx or u prime? What rule are you using when you say that? Chain rule. It's composite, right? So you have to multiply by the chain rule factor. And then f of a has to be a constant because f is some function and a is a constant. Whenever you plug in for a function, the output is always a constant. And so the derivative of that would be 0. You put that if you want or not. And so this would probably be the better result here, the one that would be more widely used. Okay? So you look like you're doing better. You think you're good? Okay. Let me show you an example of this. And let me show you where I'd expect you to use the trick. And I have kind of a shaky little saying to go with this, and I say it's shaky because I don't think it's the greatest saying. I'll use it if I have to. Let me show you how to do this one. So if you're looking at number 1, here's what you'd do. You'd recognize a couple of important things. Number 1, it's d dx of some antiderivative, right? So as soon as you see d dx of some antiderivative, red lights, whatever, warning bells need to go off in your brain, and you need to say, oh, this is a little bit unique, right? It's a derivative of an antiderivative. This is FTC2, Fundamental Theorem 2, and I want you to use this Fundamental Theorem 2 trick. And here's what you do. Wouldn't this cancel with this? Derivative, antiderivative, they cancel each other out. Then what you do is you take the upper limit, you drop it in for the t, that's right. So it'd be e to the x squared cubed, and then you multiply by the derivative of what you dropped in. So you'd multiply in this case by 2x. This.
Wouldn't it be, because in the other times it was just x at the
Oh, what
top.
you dropped in.
Say again?
Because the other times when it's just x at the top, you are doing that, but you're just multiplying it.
Times 1. Yep, exactly right. That's exactly right. So that's the chain rule factor right there. So I'll say my saying. I'm not particularly proud of it. It's not that great. So FTC2, here's the trick. Drop and derive. You get it?
Yeah.
Drop it in and derive.
I like it.
This mathematically is pretty terrible, but whatever. Drop and derive. So you just, the d dx and the antiderivative cancel each other out. You drop in that upper limit, and then you multiply by the derivative. Drop and derive. Yes, ma'am.
This is a really stupid question, but that would be e to the x to the 6th, right?
So that is not a stupid question. That's not a stupid question because you are not the only one that has it, I'm quite sure. You have x to the 2 to the 3. Whenever you have a base to a power, you
Multiply.
do multiply. Yep. So e to the x to the 6th times 2x. So you could simplify that. Oh, yeah, go ahead.
It's only the top limit.
Yeah. Yeah, so if you had... Let me ask you this. What if you saw something like this? This is a little bit different. What if you had... What would you do here? D dx of the integral from, I don't know, 5x cubed to 4 of sine squared of t. Yeah, like in order for this to work, the lower limit needs to be a constant and the upper limit needs to be some function. And so you'd flip your limits and make it negative. Yeah. So what I was pointing out here is notice how with this FTC2 trick, notice how the upper limit is a variable and the lower limit is a constant.
Yeah.
Upper limit is a variable, lower limit's a constant. Notice here how the lower limit is a variable and the upper limit is a constant. In order to use the FTC2 trick, you'd have to flip and change the sign. And then you could just use the trick. Then you could drop and derive.
Oh, so it's just negative.
It would just be the opposite. Yep, the negative of it. Yep.
So this is a stupid question, but why would there be a derivative of an antiderivative?
Because if you have, did you watch the video?
I watched, yeah, kind of.
So if you have an accumulation function, which is what that is, the integral from a to x of f of t, and you're looking to find its rate of change, you're going to be doing a derivative of it.
Okay.
That's kind of the short answer. You'll see some more examples coming up. You will. Hey, if you guys would, please try number 2. If you're starting to get this, I hope this number 2 will just take you a moment to try. Ready, go. Here's the hope, that you would look at something like number 2, and you would notice that you're doing the derivative of an antiderivative. You'd see these two symbols here, and you'd think, oh, wait a minute, this is that FTC2 thing. So a piece of this is definitely recognition. You want to see d dx of an integral or integral of d dx and recognize those two things are going to cancel each other out. You've got FTC2 right here. So whenever you're going to be executing FTC2, please, for goodness sake, I hope you're listening, do not try to find the antiderivative of sine of t squared. You won't be able to do it. It's beyond you right now. Okay, so don't even bother trying. The same thing with don't even bother trying to find the antiderivative of e to the t cubed. It's way beyond us right now. Don't even bother. Please, for goodness sake, use the trick. Okay, so the trick is this and this cancel out. You drop and derive. You get something like that. So you could write it as 2 sine of 4x squared if you wanted to. What do you guys think?
Beautiful.
Do you see how, if you know this trick, these are not that hard? I hope you see that. I hope you can see it simply. It's drop it in, multiply by the derivative. Drop and derive. Okay. Questions, concerns, anything I can do to help? Okay, so this is where I think 4.4 gets really, really fun. We're going to be doing everything more or less contextually from here on out. And so this last part of 4.4, which we will spend the rest of our week on, is called the net change theorem. And the net change theorem has one really basic meaning that will apply to a lot of different situations. So guys, if you want to sum up the next 3 days, more or less, here's what it is. The definite integral of the rate of change gives the net amount of change.
Yes.
The definite integral of a rate of change gives you an amount of change. So the two words at play here are rate and amount. So the definite integral of a rate will give you the amount of change. Let's think this over. Think about velocity for a second. What is the antiderivative of velocity? Position. So if I were to write this out using my fundamental theorem of calculus, I would say that this equals x of t, x for position, is that all right? Evaluated from a to b. So I could say that the integral from a to b of v of t dt equals x of b minus x of a. Well, if x really means position, wouldn't x of b be like your second position? And x of a would be your first position? Isn't this, then, change in position? Does that make sense? So the definite integral of a rate gives you an amount of change.
So that would be the amount of change of velocity.
No, it'd be the amount of change of position.
Because I was going to say, where does the time...
Well, b and a are times.
Oh, I see.
Two different times.
Velocity would give you the amount of change for position. Like,
The definite integral of velocity gives you the amount of change of position.
if
yep.
you wanted velocity, you do the definite integral of acceleration.
If you wanted the amount of change of velocity, yes, definitely.
Because it's the rate of change of.
Velocity. Yep, exactly. Does anybody know what change of position is? Like there's a term, like a single word term for it. Change in position. Displacement. I thought I heard a couple of you. It was like I heard a bunch of displacement. Shout it out. It's okay. So yes, this is displacement right here. So then, leaky tank, the water tank, right? So what if you have a tank that is leaking at L of t? Okay, so the definite integral from a to b of the rate of this leak is going to give you the amount that leaked out. The amount that leaked out.
They have to say that, like, because velocity is like.
Yeah, I would have to tell you that
Would it have
L
to
stands
say,
for
like,
the rate of
would it
change
have
of.
to say like the rate of leak? Like you can't. Would it just?
Like it would tell you that L of t is the rate that the water is leaking out, or something like that. Let's think about the units here. What kind of units would go with L of t maybe?
Drops per second.
Drops per second. It's pretty good.
Drip.
What else? Well, how else do we measure stuff in a tank? Say again? Ounces per, well, so it would, so she said drops per second,
These all sound a lot more educational.
ounces per something, gallons per something. What does the per something have to be? Time, right? Seconds,
Amount per time.
minutes, that's right, hours, whatever it is. So if you do the definite integral of drops per second, that'll tell you the number of drops that leaked out.
For how long? In 1 second?
Well, depending on what A and B are.
So A and B would be two different times.
Mm-hmm.
Okay.
Yeah, so if A is 0 and B is 12, it would be over the course of those 12 seconds. Yep. So the general principle is the definite integral of a rate is going to give you the amount of change. So again, the word play here that's really important to realize is that we are talking about the definite integral of a rate will give you an amount of change. And so units come into play here. The concept of rate versus amount is important. Okay, so if you guys would, please take a look at number 1. This might be the only example we do. I think this will for sure be the only example we do. It says gasoline flows out of a storage tank at a rate of R of t gallons per hour, and the graph of R of t is shown below. If the tank contained 1,150 gallons of gas at t equals 0, write an expression for the amount of gas in the tank at time t equals 3. From left to right, the areas given are 150, 100, and 75.
So would you do the little squiggly S?
So little squiggly s. Okay, so integral from
0 to 3.
0 to 3.
And then L.
What does L of t stand for?
R, T, sorry.
R of t? Sure. So that's the definite integral of a rate.
But what would you label? It's like anti-derivative as.
So we don't really have to do that because we don't have a rule for it. I mean, you could maybe call it capital R of t, but I don't, because of the information that we're given, I don't think we need to go that far.
Okay.
What could we use to evaluate that integral?
What's the graph?
What about the graph?
Well, because we have the area.
We have the areas, right?
Areas.
We have the areas. Okay, so then we could say that this equals what? Say again? No.
It would be negative 125.
Uh,
Oh,
well,
wait, sorry, I thought.
let's just do it piece by piece. What would be the first piece?
I thought this one.
Negative 150 plus 100. Yep, minus 75. So any areas above the t-axis would be considered to be a positive accumulation. Any areas below would be considered negative accumulation. And so negative 125? Okay, so let's see if we have answered the question. It says, write an expression for the amount of gas in the tank at t equals 3. So are there negative 125 gallons in the tank at t equals 3? You can't have negative gallons of gas.
Oh, would you do like R of 3 minus R of 0? And because you know those.
Well, so it would have to be capital R of 3, right?
Yeah.
Okay, so guys, let's go back. What if we said this? Capital R of 3 minus capital R of 0. That would be amount at 3 minus amount at 0, right? Equals negative 125. How has this helped us?
Because we know the amounts at those points.
Almost. We know the amount at 0. What is the amount when t equals 0? 1150. Yep, so we could say R of 3 minus 1150 equals negative 125. And then what would we do?
Know that the other one.
Just add over, right? You just add that 1150 over. So if you add 1150 to both sides, you'd get the amount at 3 equals what? 1025? So if all we did was this, we're forgetting that there was water in the tank to begin with, right? Hey guys, listen up. Here is where there's sometimes a challenge. This negative 125 is not the amount of water in the tank. This is the change in the amount. So back to the height analogy. Now this would be improbable, but if I told you, if I saw you tomorrow and I said, guys, you won't believe this. Last night, I grew an inch. I'm an inch taller than I used to be. Does that mean that I'm 1 inch tall? No. What does it mean? The change was 1 inch. My new height would be whatever I was yesterday plus that inch, right? And so don't confuse change with amount.
Or wouldn't it be R of what you were yesterday? Or
Plus-
like R of what you are today minus R of what you were yesterday equals 1?
Yes, technically, but then you just add that over. Yes, definitely. Hey guys, one thing I want to bring up to you real quick in our final, I was going to try to make this happen in 1 minute. If you've looked ahead, I mistimed it by about 3 minutes. So hang on 1 second. So this is,
Will you give us our quizzes sometime soon?
I will. The only issue is there were 8 people that didn't take it. So we've got a decent number of them scheduled. I'm probably going to hand them back to you next time.
Okay.
Unless you're just dying to see it.
Yeah.
Hang on 1 second.